Hello, everybody. You see my screen? So hi, everybody. I'm Gianmario, and I'm the founder of the community of Data Science Milan. I guess today there are some new members. Generally, I ask people to raise their hand during the physical events. I can't do that, but I guess I received a lot of emails of people that just registered on Meetup. So I guess that some of you are new. I would like to spend just 5 minutes introducing you to the community and what we do. We are a group that was founded on February 2016, so it's more than 4 years. We are a technical community. Currently, we have more than 1.5 thousand members, and we generally meet every month, whether it's a physical event or an online event like this one. This is the staff. Those are the people that are behind the organization. You probably gonna find them in the list of participants, or you can talk with them on Slack. I'll give you details about how to join our Slack channel. The next slides. Everything that we do, and all the links, all the resources, everything is gonna, you can access it through our website, datasciencemilan.org. And in particular, I recommend everybody that if you have not done this yet, to go on our website. This is our website. And here you can find both the links to all of the previous events and our blog. But you're also gonna find, if you scroll down to the bottom, you're gonna find Get in Touch. And here there's a link to join Slack. So Slack is essentially our tool that we use for keeping in touch with each other. So you're gonna find, not everybody is on Slack, but a lot of members are on Slack every day. And we're also gonna use this tool for asking questions to the speaker. Because, you know, if 100 people start talking and start asking questions, it's gonna be a mess. So we kindly ask you to go on Slack, write your question there, or just reserve your question. Then someone will facilitate and will ask you to, will ping you and ask you to, speak loud about the question you want to do to the speaker. Let's move on. So as I say, there is a blog where you can find articles about all the previous events, like summaries of the previous events. And there is a monthly digest we send once a month. Again, you can go on the website, you can find the section for registering. You're gonna receive this email just once a month with all of the relevant information about industry news and events, both locally in Milan, but also events generally in Europe about data science and machine learning. Slack, and then if you want to submit a talk, we are always open. We work with every company, everybody who wants to propose anything that is relevant to our topics. Please send us your proposal. You can even, it can be through the form, the official form. You can just go on the chat on Slack and just write, ping one of the member of the staff, and just you can talk privately. Data Science Milan is part of the Italian Association of Machine Learning, and we thank the association because they gave to us the tools for doing the meet, for streaming this event. Otherwise, it wouldn't be possible without them. So we thank them again. We also would like to promote a couple of other webinars that are happening this week and next week. It's part of the Hack at Me Digital Arena. There's one talk about the European Space Agency, which is going to be this Thursday. And then there's another talk next Thursday about ethics and social good, like how to use AI for social good. You can find those more details on hackat.it. If you want to promote any project, you want any message you would like to share with the community, you can send us your correspondence, and then we'll make sure to include that in one of the next event, or we can include that in the newsletter. Okay, so this is the agenda for today. We're gonna have Marco Del Prade, who is gonna talk about the time series classification using deep learning. I don't recommend you, I prepared this slide before, but I don't recommend you to join the stream. So if you know anybody that is struggling to enter, to watch this webinar on the stream URL, please tell him or her to join on the Meet video conference instead. So don't use the stream link. Very important for us is that with all of this, we are volunteers, so we don't ask money, we don't make money, just do it because we're passionate about. So in exchange, we ask you if you can help us spreading the word. So we want other people to know what we do. So you can find us on Twitter, Facebook, LinkedIn, and on YouTube, where we generally publish the recordings of the events after each event. We are publishing there. So please share and like what we publish. If you want to take any snapshot, any pictures today during the event, feel free to do that. Okay, that's it. I will now ask Marco to introduce himself and give us the talk of the evening. Thank you very much. Marco, you're muted.
Just a second. Hi, everybody. My name is Marco Del Pra. I live in Milano, and I work in data science.
Marco, you are muted again. Somebody muted you. Please don't mute the speaker. Be polite.
Do you hear me now?
Yes, at least I do.
Yes. Okay. Hi, everybody. My name is Marco Del Pra. I'm 41 years old, and I live in Milano, and I work in artificial intelligence since 10 years. And in the last years, I also worked for Microsoft and for Cubic. Today, I will speak about time series classification with deep learning. First of all, I want to underline why this problem is so important today, and therefore why it is very interesting to understand the role and the potential of deep learning in this sector. During the last years, time series classification has become one of the most challenging problems in data mining. This happened because any classification problem that uses data, taking into account some notion of ordering, can be treated as a time series classification problem. Time series are present in many real-world applications, ranging from healthcare, cybersecurity, finance, marketing, and so on. And with the increase of temporal data availability, many areas are strongly increasing their interest in application based on time series. And then many algorithms have been proposed. All these algorithms, apart from those based on deep learning, require some kind of engineering as a separate task before the classification is performed. And this can imply, of course, the loss of some information and the increase of the development time. On the contrary, deep learning models, such as recurrent neural networks or convolutional neural networks, already incorporate this kind of feature engineering internally, optimizing it and eliminating the need to do it manually. Therefore, they are able to extract information from the time series in a faster, more direct, and more complete way. Now, what is time series classification problem. Let us consider some examples. Electrocardiogram records can be used to find out various heart problems, and they are saved in time series form. Distinguishing the electrocardiogram of a normal heart from the one of a heart with a disease and recognizing the disease is a time series classification problem. Today, many devices can be controlled with the use of simple gestures without physically touching them. For this purpose, these devices record a series of images that are used to interpret the user's gestures. Identifying the correct gesture from the sequence of images is a time series classification problem. Anomaly detection is the identification of unusual events or observations which are significantly different from the majority of the data. Often, the data in anomaly detection are time series. For example, the temporal trend of a magnitude related to an electronic device, monitored to check that the device is working correctly. Distinguishing the time series of normal operation from that of a device with some anomaly and recognizing the anomaly is a time series classification problem. Now, let us give a formal definition of time series classification problem. Suppose to have a set of objects with the same structure, for example, real values, vectors, or matrices with the same size, and a fixed set of different classes. We define a dataset as a collection of pairs object class, which means that to each object is associated a determinate class. Given a dataset, a classification problem is building a model that associates to a new object with the same structure of the others the probability to belong to the possible classes, accordingly to the features of the object associated to each class. This is about the classification problem. To go to a time series classification problem, we need to make some more definitions. An univariate time series is an ordered set of real values. An m-dimensional multivariate time series consists of m different univariate time series with the same length. A time series classification problem is a classification problem where the objects of the dataset are univariate or multivariate time series. Before introducing different types of deep learning architecture, we recall some basic structures that they use. First of all, we introduce the perceptron, that is the basic element of many machine learning algorithms. It is inspired by the functionality of biological neural circuits, and for this reason is also called neuron. The first figure shows the architecture of a perceptron. A perceptron has one or more input values, and every input value is associated to a weight, like we see in the figure. The most common activation functions are sigmoid, hyperbolic tangent, and rectifier that are illustrated here. The result of the activation function is referred as the activation of the perceptron and represent its output value. Now we introduce the multi-layer perceptron. That is a building block used in many deep learning architectures for time series classification, including those that we will see later. A multi-layer perceptron is a class of feed-forward neural networks. As we can see in the figure, they consist of several layers of nodes. The input layer, the hidden layer, that can be one or more, and the output layer. Every node is connected to all the nodes of its layer, of the previous layer, and of the next layer. For this reason, we say that the multi-layer perception is fully connected. Each node of the hidden layers and of the output layers is a perceptron. Hence, the output of the multi-layer perceptron is obtained computing in sequence the activation of its perceptrons. And the function that connects the input and the output depends on the values of the weight. Multi-layer perceptron is commonly used as for classification problems. Given a dataset that we call to be a collection of pairs object class, it can be fitted to compute the probability of any object or of any new object to belong to each possible class. To do this, first of all, we need to represent the pairs object class in a dataset in a more suitable way. Every object must be flattened and then represented with a vector. That will be the input for the training. Each class in the dataset must be represented with the one-hot label vector. What is a one-hot label vector? A one-hot label vector is a vector with size equal to the number of different classes in the data. Each element of the array corresponds to a possible class, and every value is zero, apart from that related to the represented class, that is 1. The one-hot label vector will be the target for the training. We can see a simple example of one-hot label vector in the figure. In the original dataset, the column class has 3 different values. And in the dataset with the one-hot label vector, there are 3 columns, 1 for each class. Hence, we obtained a new dataset of pairs, input vector target. And we are ready for training. For this process, multi-layer perceptron uses a supervised learning technique called backpropagation, which works iterating on the input vectors of the dataset. At every iteration, the output of the multi-layer perceptron is computed using the present input vector. And the output is a vector whose components are estimated probabilities of belonging to each class. The model's prediction error is computed using a cost function. And then, using gradient descent, the weights are updated in a backward path to propagate the error. Thus, by iteratively taking a forward pass followed by a backpropagation, the model's weight are updated in a way that minimizes the loss on the training data. After the training, when the input of the multi-layer perceptron is the vector corresponding to an object with the given structure, also not present in the dataset, the output is a vector whose components are the estimated probabilities of belonging of the object to belong to each class. Now, a natural question is, why don't use the multi-layer perceptron for time series classification, taking the whole multivariate time series as input? The answer is that multi-layer perceptors, as many other machine learning algorithms, don't work well for time series classification, because the length of the time series really hurts the computational speed. Hence, to obtain good results for time series classification, it is necessary to extract the relevant features of the input time series and use them as input of a classification algorithm in order to obtain better results in a very lower computational time. The big advantage of deep learning algorithms with respect to the other algorithms is that these relevant features are learned during the training and not encrypted. This improves very much the accuracy of the results and makes the data preparation much lower. The data preparation time, I mean, much lower. Then, after many layers are used for the extraction of these relevant features, many deep learning architectures can use algorithms like multi-layer perceptron to obtain the desired classification. Then here we see a general deep learning framework for time series classification. As we see, the input is a multivariate time series. A deep learning algorithm is composed of several layers that implement nonlinear functions. Every layer takes as input the output of the previous layers and applies its nonlinear transformation to compute its own output. The behavior of this nonlinear transformation is controlled by a set of parameters for each layer. These parameters link the input of the layer to its output and are trainable, like, for example, the weights in the multi-layer perceptron. Often, the last layer, as we already said, is a multi-layer perceptron, or for example, it's a regressor or softmax. In the following slides, I will present 3 different deep learning architectures for time series classification. The convolutional neural network that is the most classic and used architecture for time series classification problem. Inception time, that is a new architecture based on convolutional neural networks, and echo state network. That is another recent architecture based on present neural networks. Then, now we speak of convolutional neural networks. A convolutional neural network is a deep learning algorithm that takes as input an image or a multivariate time series, is able to successfully capture the spatial or temporal patterns through the application of trainable filters, and assigns importance to these patterns using trainable weights. The pre-processing required in a convolutional neural network is much lower than as compared to other classification algorithms. While in many methods filters are hand-engineered, convolutional neural networks have the ability to learn these filters, as we already mentioned. A convolutional neural network, as you see in this image, is composed mainly of 3 different layers: the convolutional layer, the pooling layer, and the fully connected layer. Usually, several convolutional layers and pooling layers are alternated before the fully connected layer, as we can see here in the image. The convolutional, now we speak of all the 3 different layers of the main layer of the convolutional neural networks. The convolution operation gives the name to the convolutional neural network because it's the fundamental building block of this type of network. It performs a convolution of an input series of feature maps with a filter matrix to obtain an output, as output a different series of feature maps, with the goal of to extract the high-level feature. The convolution is defined by a set of filters that are fixed sign matrices. When a filter is applied to a submatrix, we can see what happens in this figure. The output is of the application of the filter with the submatrix is given by the sum of the product of every element of the filter with the element in the same position of the submatrix, and you can see this in the figure. The result of the convolution between one input feature map and one filter is the ordered feature map obtained applying the filter across the width and the height of the input feature map, as shown in the figure. As you see, first I apply the filter to this red square, then to the blue one, then I shift and I apply to the pink one, and the results are put in order. A convolutional layer executes the convolution between every filter and every input map, obtaining as output a series of feature maps. As already underlined, the values of the filters are considered as trainable weights, and then are learned during the training. Two important parameters that must be chosen for the convolutional layer are the stride and padding. Stride controls how the filter convolves around one input feature map. In particular, the value of stride indicates how many units must be shifted at a time. How we can see in the figure, you see that when the stride is equals to 1, the input of the convolution is shifted of 1 position to the right. When the stride is equal to 2, the convolution is shifted by 2 positions on the right. The same we can do from top to bottom. The other parameter is padding. Padding indicates how many extra columns and rows to add outside an input feature map before applying a convolution filter, how we can see in this figure. All the cells of the new columns and rows have dummy values, have a dummy value that is usually 0. Padding is used because when a convolution filter is applied to an input feature map, its size decreases. Then, after the application of many filters, the size can become too small. Adding extra rows and columns, we can preserve the original size or make it decreasing slower. When the size of the feature map obtained after the application of the convolutional filter is smaller than the size of the input feature map, we call this operation valid padding. When the output size is equal or greater of the input size, we call this operation shrink padding. Now we speak about the second important layer of the convolutional neural networks, that is the pooling layer. The purpose of the pooling layer is to achieve a dimension reduction of future maps, preserving as much information as possible. It is useful also for extracting dominant features which are rotational and positional invariant. Its input is a series of future maps, and its output is a different series of future maps with lower dimension. Pooling is applied to sliding windows of fixed size across the width and the height of every input feature map. There are two types of pooling, max pooling and average pooling. As we can see in the figure, for every sliding window, the result of the pooling operation is its maximum value or its average value, respectively for max pooling or for average pooling. We can see here in the map. I take the sliding window, I take the maximum, and I put the maximum in the result. And I go on in this way. Max pooling works also as noise suppressant, discarding noisy activations altogether. Hence, it usually performs better than average pooling. Also, for pooling layers, stride and padding must be specified. The advantage of pooling operation is downsampling the convolutional output bands, thus reducing variability in hidden activations. Then the last layer of a convolutional neural network is the last main layer, let's say. Is the fully connected layer. The goal of the fully connected layer is to learn nonlinear combination of the high-level features represented by the output of the convolutional layer and the pooling layer. Usually, the fully connected layer is implemented with a multi-layer perceptron, but it can be also a ridge regressor or softmax or so. After several convolution and pooling operations, the original time series is represented by a series of feature maps. All these feature maps are flattened into a column vector that is the final representation of the original input multivariate time series. The flattened column is connected to the multi-layer perceptron, whose output has a number of neurons equal to the number of possible classes of time series, like we have already seen for multi-layer perceptron. The backpropagation is applied to every iteration of training over a series of epochs. The model is able to distinguish the input time series thanks to their dominant high-level features, and then to classify them. Now, which are the most important hyperparameters of convolutional neural networks? There are many parameters, hyperparameters for convolutional neural networks. So we speak only about the most important. The number of convolution filters, obviously. Too few filters cannot extract enough features to achieve classification. However, more filters are helpless when the filters are already enough to represent the relevant features and make the training more expensive from a computational point of view. The convolution filter size, and initial values. Smaller filters collect as much local information as possible. Bigger filters represent more global, high-level, and representative information. The filters, the values of the filters are usually initialized with random values. What about pooling method inside? As already mentioned, we have two types of pooling, max pooling and average pooling. And max pooling usually performs better since it works as noise suppressant. Also, the pooling size is an important parameter to be optimized since if the pooling size increases, the dimension reduction is greater, but of course, the more information are lost. The weights are usually initialized with small random numbers to prevent their neurons, but those numbers should be not too small to avoid the zero gradient. Uniform distribution usually works well. Activation function introduces the nonlinearity in the model. As we have already seen, rectifier, sigmoid, or hyperbolic tangent are usually chosen. The number of epochs is the number of times the entire training set passed through the model. This number should be increased until there is a small gap between the test error and the training error, of course, if computational performances allow it. Now, how can we implement a convolutional neural network? Building a convolutional neural network is very easy using Keras. Keras is a simple-to-use, powerful deep learning library for Python. To build a convolutional neural network in Keras are sufficient few steps. First of all, declare a sequential class. Every Keras model is either built using the sequential class, which represent a linear stacks of layers, or the model class, which is more flexible. Since a convolutional neural network is a stack of linear stack of layers, we can use the simpler sequential class. Then we have to add the desired convolutional max Boolean dash Keras layers that are already implemented in Keras in the sequential class, and specify the number of filters and the filter size for the convolutional layer and the pooling size for the pooling layer. And then we have already built a convolutional neural network. To compile this model, Keras needs more information that are the input shape, and there is to say that once that the input shape is specified, Keras automatically infers the shape of the inputs for the later layers. Then the optimizer, that for example can be a stochastic gradient descent or Adagrad. The loss function, for example, the mean squared error or the mean absolute percentage error. And a list of metrics, for example, the most used is accuracy, of course. Training a model in Keras is literally consists only in calling the function fit, specifying the needed parameters that are the training data, the number of epochs, and the validation data, which are used during the training to periodically measure the network performance against data it hasn't seen before. Using the trained model to make the prediction is easy. We pass an array to an input of input to the function predict, and it returns the array of output. This is, of course, the same like in SciPy, sklearn, scikit-learn, and so on. Now, the main difficulty in using the convolutional neural network is that the length of time series can slow down training. and the result can be not accurate as expected with chaotic input time series or with input time series in which the same relevant feature can have different sizes. To solve this problem, many new algorithms were elaborated. Among these, inception time and echo-state network perform better than the others. So now we speak about inception time architecture. Recently was introduced the reception time that is derived from convolutional neural network. This kind of network shows high accuracy and very good stability. The architecture of an inception network is similar to the one of a convolutional neural network, with the difference that convolution layers and pooling layers are replaced with inception modules. We will speak in the next slide more in detail of inception module. As shown in the figure, the inception network consists of a series of inception modules followed by a global average pooling and a fully connected layer that usually can be a multi-layer perceptron, but as usual can be also a ridge regression and so on. Moreover, a residual connection is added every 3 inception modules. We can see here. Each residual block's input is transferred via shortcut linear connection to be added to the next block's input, thus mitigating the vanishing gradient problem by allowing a direct flow of the gradient. So we already said that the major building block of the inception network is the inception module that is shown in this figure. It consists of 4 layers. The first layer here is the bottleneck. This layer reduces the dimensionality of the input. This reduces also the computational cost and the number of parameters, speeding up the training and improving generalization. The second major component of inception module is a set of parallel convolutional layers of different size, acting on the same input feature map. For example, here in the figure, we see that the convolutional filter size are 10, 20, and 40. The third layer is the max pooling that introduces the ability of having a model that is invariant to small perturbation. As we already seen, max pooling works as noise suppressant. The fourth layer is a depth concatenation layer where the output of each independent parallel convolution and max pooling is concatenated to form the output multivariate time series of the current inception module. By stacking multiple inception modules and training the filters via backpropagation, the network is able to extract latent hierarchical features of multiple resolution. And this is thanks to the use of filters with different sizes. Thus, this is the big advantage of inception modules, since it allows the internal layers to pick and choose which filter size is relevant to learn the required information. And this is very helpful to identify high-level features that can have different sizes on different input feature maps. The key parameter to understand an inception network is its receptive field. Unlike fully connected networks, a neuron in the inception network depends only on a region of the input feature map. Like also, this is true also for convolutional neural networks, of course. This region is called receptive field of the neuron, CS of the neuron. Clearly, bottom layer neurons depend on regions that are smaller than those of top layer. Then, bottom layer neurons are expected to capture the local structure of time series, while the top layer neurons are expected to identify more complex patterns. For time series data, the receptive field of an inception network is defined from this formula. that, as you can see, depends only on the length of the filters and on the depth of the network, where the depth of the network is the number of inception modules. It's very interesting to investigate how the accuracy of the inception network changes as the receptive field varies. To vary the receptive field, we can change the filter of the length, the filter length and the depth of the network. This first figure shows the inception network's accuracy over a simulated dataset with respect to the filter length as well as their input time series length. From the chart, it's evident that a longer filter is required to produce more accurate results. This is explained by the fact that longer filters are able to capture longer patterns with the higher probability than shorter ones. This second figure shows the inception network's accuracy over a simulation dataset with respect now to the network depth, as well as the length of the input time series. It turns out that increasing the receptive field by adding more layers doesn't necessarily give an improvement of the network's performance, especially for datasets with a small training set. Hence, these results suggest that in order to improve accuracy, it's better to increase the filter length instead of adding more layers. Another important aspect is that some experiments have shown that a single inception network sometimes exhibits high variance in the accuracy. This is probably because of the variability given by the random weights in initialization. In order to overcome this instability, generally inception time is implemented as an ensemble of many inception networks, and every prediction has the same weight. In this way, the algorithm improves its stability and shows the already mentioned high accuracy and very good stability. In particular, different experiments have shown that its time complexity grows linearly with both the training set size and the time series length. And this is a very good result because many other algorithms grow quadratically with respect to the same magnitudes or also more than quadratic. Now, how to implement an inception time? A full implementation of inception time can be found on GitHub. The implementation is written in Python and uses Keras. This implementation is based on three main files. The main file contains the necessary code for run an experiment. The inception file contains the inception network implementation. And the NNE file, that means neural network ensemble, contains the code that ensembles a set of inception networks. In particular, the implementation uses the already mentioned Keras module class, since some layers of the inception time work in parallel, unlike convolutional neural network that, as we have already seen, uses the sequential class, since the layers are in parallel in a series. The code that implements the inception module building block is very similar to that described for convolutional neural networks. It uses Keras layers for convolutional and mask pooling. Hence, it can be easily used or included in code based on Keras in order to implement customized architectures. The structure of the code that implements the compilation, the training, and the use of the model is very similar to the one described for convolutional neural networks, and it's also similar, as I already said, to SciPI, scikit-learn, and so on. Okay, so this is about inception time. What about echo state network? First of all, echo-state network is a type of recurrent neural network. Hence, first of all, I give an introduction about them. Recurrent neural networks are networks of neuron-like nodes organized into successive layers with an architecture similar to the one of standard neural networks. In fact, like standard neural network, neurons are divided in input layer, inner layer, and output layer. And each connection between neurons has a corresponding trainable weight. The difference is that in this case, every neuron is assigned to a fixed time step. The neurons in the hidden layer are also forwarded in a time-dependent direction. That means that every one of them is fully connected only with the neurons in the hidden layer with the same assigned time step. And is connected in a one-way connection to every neuron in the assigned to the next time step. How as you can see here in the figure. The neurons on the first hidden layer are connected in a one-way direction to the neurons of the second hidden layer. The input and the output neurons are connected only to the hidden layers with the same assigned time step. So now, since the output of the hidden layer of one time step is part of the input of the next time step, the activation of the neuron must be computed in time order. At any given time step, only the neurons assigned to that time step compute their activation. So this was a very brief introduction about neural networks, recurrent neural networks. Also because recurrent neural networks are rarely applied for time series classification, mainly due to three factors. This type of architecture is designed mainly to predict an output for each element in the time series. When trained on long time series, recurrent neural networks typically suffer from vanishing gradient problem. That means that the parameters in the hidden layers either don't change that much, or they lead to numeric instability and chaotic behavior. The third reason is that the training of a neural network is hard to parallelize, and is also very expensive from a computation point of view. Echo-state networks were designed to mitigate the problems of recurrent neural networks by eliminating the need to compute the gradient for the hidden layers, reducing the training time and avoiding the vanishing gradient problem. In fact, many results show that echo-state networks are really helpful to handle chaotic time series. Now, this is the architecture. This is the architecture of an echo-state network. It consists, as you can see, in an input layer, a middle layer that is called the reservoir, a dimension reduction layer, a fully connected layer that is called a readout, and an output layer. The reservoir is the main building block of an echo-state network. We will see it in detail in the next slide. But mainly it is organized like a sparsely connected random recurrent neural network. The dimension reduction algorithm is usually implemented as a principal component analysis. The readout is usually implemented as a multilayer perception, a read regress, a softmax function, and so on. The weights between the input layer and the reservoir are those in the reservoir are randomly assigned and not trainable. This is very, very important. The weights in the reservoir are not trainable, and they are totally random. The weights in the readout are trainable, so that, okay, in this way, the network can learn somehow to reproduce the specific patterns. Now we see in detail how the reservoir works. As already mentioned, it is organized like a sparsely connected random recurrent neural network. The reservoir is connected to the input layer and consists in a set of internal sparsely connected neurons and its own output neurons that are here. The input neurons are the input neurons of the whole echo state network, and those are the output layers of just the reservoir layer. As you can see, there are 4 types of waves. The input waves between the input layer and the internal neurons that you can see here. The internal waves that connect the internal neurons to each other, they are here. Then the output waves between the internal neurons and the output. And then the back propagation wave that connect back the output to the internal neurons, they are here. All these waves are randomly initialized, are equal for every time step, and are not trainable. This output is added to the total reservoir output, but acts, the output of the reservoir for each time step is added to the total reservoir output, but acts also as input for the next time step, since it is connected back to the internal neurons with the back propagation wave. So this is why the reservoir works as a recurrent neural network. Like in recurrent neural network, the output of the reservoir is computed separately for every time step, since, of course, the output of a time step is part of the input of the next time step. At every time step, the activation of every internal and output neuron is computed, and then the output for the current time step is obtained. Then we can say that the big advantage of echo state network is that the reservoir creates a recurrent nonlinear embedding of the input into a higher dimensional representation. But since the waves in the reservoir are not trainable, the training computation time remains low. Now, many experiments show that choosing the correct dimensional reduction is possible. It's important to reduce the execution time without lowering the accuracy. Moreover, dimensional reduction provides a regularization that improves the overall generalization capability and robustness of the model. This figure shows how the training time and the average classification accuracy of an echo state network vary with respect to the subspace dimension after dimension reduction, of course, for a particular experiment. For these experiments, but also for other experiments, it turns out that the training time increases almost linearly with the subspace dimension d, while it is evident that in this case, accuracy stops growing around d equal to 75. Hence, in this case, the better value for the subspace dimension would be 75, because with the higher subspace dimension, we would have a longer execution time without any relevant improvement in the accuracy. A full implementation of Python, a full implementation in Python of echo state network is available on GitHub. The code uses the library scikit-learn and scipy. There is no TensorFlow, no dependency on TensorFlow. The main class, RC classifier, contained in the file modus.py, permits to build, train, and test a reservoir classifier, that is the family of algorithms that to which the echo state network belongs. The hyperparameter requested for the reservoir must be optimized in order to obtain the desired accuracy and desired performance for execution time, of course. The most important are the number of neurons in the reservoir, the percentage of non-zero connection weights, that usually is less than 10%, and the largest eigenvalue of the reservoir matrix of connection weight. The most important hyperparameters in other layers are the algorithm for dimensional reduction that, as we already said, can be known or can be the potential principal component analysis for multivariate time series data. The subspace dimension after the reduction layer, that is very important as we have already seen, and the type of readout used for classification, multi-layer perceptron, ridge regressor, or S1. Those are the three possibilities that are given by the code. The number of epochs the other, of course, important hyperparameter is the number of epochs. That is the number of iterations during the optimization. The structure of the code that implements training uses the model is very similar to the one described before for the other models. Hence, in conclusion, convolutional neural networks are the most popular deep learning techniques for time series classification, since they are able to successfully capture the spatial and temporal patterns through the use of trainable filters, and to assign importance to these patterns using trainable weights. The main difficulty in using convolutional neural networks is that they are very, very dependent on the size and the quality of the training data. In particular, as we already said, the length of the time series can slow down training, and the result can be not accurate as expected with chaotic input time series or with input time series in which the same relevant feature can have different sizes. To solve this problem, many new algorithms were recently elaborated, and among these, Inception time and state network perform better. Inception time is derived from convolutional neural network and speeds up the training process using an efficient dimension reduction in the most important building block, the inception module. Moreover, it performs really well in handling input time series in which their same relevant feature can have different sizes. Echo-state networks are based on recurrent neural networks and speed up the training process because they are very sparsely connected with most of their weights that are fixed a priori to randomly chosen values. Thanks to this, they demonstrate remarkable performances after very fast training. Moreover, they are really good and helpful to handle chaotic time series. Hence, in conclusion, high accuracy and high scalability make this new architecture the perfect candidates for the product development. And I'm done.
Thank you very much, Marco. I think you collected a lot of questions during the talk. I don't know if you can access the chat.
Just a second. Just a second. Let I access it. Just a second. Okay, where is it?
There are quite a few. I think maybe you want to go.
Okay, here we are.
Start. Yeah, you want to read them loud and.
Okay. Yeah, there are a lot of questions. Okay. What should I do? I read them. Did you read them?
Yeah, unfortunately, I cannot help you much on that because I've just joined the chat. I cannot see the chat, the previous messages. So I lost some of the questions that were asked before. So since you've been connected all the time, I think you have the whole log of.
Okay, so I can answer to the question. Okay, let me read them. So, okay. Anyone asked where we can find the GitHub repository. I will publish when we will publish the slides. There will be all the references to the papers and to the GitHub repositories. I'm reading the questions.
Do you want me to help you on reading the question? Then you can
Yeah,
answer?
but I work so. Then, which network type works better for non-stationary time series? In my experience, ecostate network, I would say, because they are the networks that works better when the input is really chaotic, and is where there are the biggest non-linearities. Okay. Just a second that I'm reading. Okay, now this is it. So George says, don't you find that doing some data preparation before feeding to a deep learning algorithm tends to decrease the training time and improve generalization performance? I feel no data prep to deep learning is a misconception. And Davide asked answer. You're right. Time series with strong trends can benefit indeed from rescaling or, in general, transformations that reduce and contains the range of the time series codomain to something close to -1, 1. Yes, of course. It depends on what you are doing, and it depends if you feel that the future that you can extract are enough to have a good result or not. Of course, some data preparation can be useful, but it really depends on the data, and it really depends on what you know about the future that it can explain what's happening. So you have to check. I mean, usually when you use when in data science, when you can use simple models, you have to use simple models. And so if you can use, if the feature that you already know how to extract are useful to get good results, you can use them. The good, the deep learning is useful when you don't know. When your results with the future that you already know are not good, and so you are going to search for more futures, for more high-level future that you didn't consider. Okay, those are seems to be the most important questions. Okay. How do others use Keras models in production? When not using Python in production? Also here it really depends. I have always seen situation in which Python is used in production, and other situation in which the production is not used. It really depends on the situation, on what is your production. I think that it's a question for which there is not a perfect answer. I mean, it really depends on the situation. I think that perhaps I answered to all the questions. I don't know if there are other questions.
I think somebody just asked some questions recently. They added some new message.
Okay. So just a second. Just a second. Okay. About long short-term memory networks, I don't think that they are good option for this task. It's a kind of recurrent neural network, but the problem is that the only reason why echo state network can be used for the time series classification is that there is no training on the reservoir, so on the recurrent neural network, because training a recurrent neural network or a kind of recurrent neural network on this kind of problem is really hard due to the reasons that I explained before. About GRU networks, to be honest, I don't know. I don't know GRUs as well to say. I didn't use them for time series classifications, and so I don't know if they can be good for this kind of problems. Okay, I see other questions.
And I would also add that if anybody wants to answer any question,
yeah,
because he wants to add,
if somebody knows GRUs networks better than me, can answer.
Yeah, if you want just a comment about GRUs, I'm not a super expert. I've never used them, but the point is that it's not a huge advance compared to LSTM in this scenario, because it's basically a simplified version of LSTM. But then again, if you have a real-time series, it's gonna be like an ECG signal, for example. It's gonna be very, very hard to train this. The same as an LSTM, I would say.
If anybody wants to answer the other questions also, please.
Okay, sorry, I was
sorry, I didn't want to interrupt you. I was just saying that, of course, the questions are mainly referred to our speaker, but of course, if anybody wants to add any other answer, any other comment about any question that we said so far, please say that.
So I would, in the meantime, I would like to answer to a very interesting question. That is, could you think about using these models to financial time series, for example, in the trading market? Yes and no. No. I am actually working on using machine learning trading market, so I really know well the environment. So yes or no? Why? First of all, in financial trading, the problem is more to predict output values instead of make a classification of time series. Of course, you can make classification of time series, but it's like the classification is like this this trend will be good, this trend will be not good, this trend is an anomaly, so it's not probably it will have a behavior that is that can be in, I don't know. It's about storytelling of financial trend of financial trade. Sorry, it's about the storytelling of financial time series. I mean, if you want to use machine learning for financial trading, the answer is not time series classification. The answer is reinforcement learning. Reinforcement learning allow you to have a prediction of the behavior and the trend of some series, where there are a lot of things that can happen, and how can I say, where a lot of data depends on external events. I mean, when you have very chaotic time series, like happens in trading, you have to use reinforcement learning, not time series classification. And I especially suggest fitted Q learning. Fitted Q learning is also here is a really new architecture that was recently developed, and is very good to make prediction in finance. Because I mean, time classification in finance is not useful, not to do predictions. I don't see any more.
We would all be rich by now.
Yeah, in fact, but we are not the only one that think about that. But now fitted Q learning is giving really good results in option hedging, for example. But of course, you have to. The problem is that in finance, you don't. It seems crazy, but for some kind of problems, you don't have enough data to make a good training. It seems crazy, but it's true, because for fitted Q learning, you need data that have some properties that, and in a lot of time you don't have all the information that you need, because some magnitudes are not observable. I mean, you don't really know, so you have to simulate them. This is why, for example, exists some for example, there is the Black-Scholes model or the Heston models. There are some models that permits to evaluate the magnitudes that are not observable. And I mean, this is a very big limit if you want to use machine learning, but somehow you can do that, but it's hard. Jacopo, credit question. What is the budget here? Great. It's a good question. It depends. It depends mainly from two things. The first one is if there is a sort of periodicity in your time series, and if you know if you know the future time step between a step and another. If you don't have any kind of periodicity and you don't have and you don't know how will the time step how will be the time step how can I say how does the time step behaves in the other observations, it's really hard. If there is a sort of periodicity, you can align the time series for the classification, classifying one period. I mean, I know that there is the time step is not constant, but I know that there is some periodicity. I take one period and I make the classification of periods.
Are there any other questions, or is that all? Right, Marco, I don't know, is there anything you want to share, or you think
no, I think
finished?
I shared everything that I wanted to share, but
Quite a lot, I would say, more than what we
Thank you.
expected. So I want to remind everybody that Marco is going to be available probably on Slack, I guess. I think you're on our Slack channel. In addition, we are going to publish the streaming on YouTube. Give us a few days. And you'll also find the slides published on our website. So check the website in 3-4 days max, and you'll find everything. And if you have not joined, if you're not registered on Meetup, then you can register. You can get invitation for the next events. That's it. And thank you very much again, Marco. Thank you everybody for joining this web meetup. See you next time.
Thank you, everybody.
Ciao, ciao.
Ciao.